Okay, so for this class, we're talking about efficiency, and that's really the main thing that we care about when we're measuring the energy of an object, right? Or if we're engineering something and we want to create some sort of useful machine, what we're really doing is trying our best to create the most efficient machine, the one that will dish out as much energy as put into it. So the idea of how much use we can get out of a machine is really based on the first few laws of thermodynamics. The first law, otherwise known as the conservation of energy, states that energy cannot be created or destroyed, so it simply just changes from one form to another. And the second, which pertains more specifically to efficiency, is that as the disorder in the universe increases, and we say that the disorder in the universe is always increasing, potential energy is lost to heat, so no process is 100% efficient. The main idea here is that if a ball is dropped from a height of x, so over here, then it'll bounce back to a different lower height of y. And the reason why it doesn't bounce back all the way to the original height that it was dropped at is because this gap in energy was lost to heat. And so while some balls might get close to the original height, so they might go here and another one might even go very close, it'll never actually go to the original height over here because some of the energy is always going to get lost to heat. And the energy we're talking about specifically here is potential energy. And so what we would say is, based on the bounce back height, so this one, and this one, and this one, all of these would have different efficiencies. And the one with a higher bounce back height would have a higher efficiency. So let's say we have a situation here where we're dropping two different balls from the same height. We'll call it ball A and ball B. They're both dropped at a height of 8 meters. Ball A bounces to about here. So let's say we draw the ball. This is the bounce back height after it's dropped. And let's say that height is about 5.0 meters. Now ball B, same thing. Let's say it goes all the way up to here, so still less than the original height. And let's say that the bounce back height for this one is going to be 6.5 meters. Well, since they were both dropped from the same height, this height over here is the input energy. And the bounce back height would be the output energy. And so we could see here that the output, right here, output of B is greater than the output of A, even though they were both dropped from the same height. So what we say is that B has a greater efficiency. Now, mathematically speaking, the efficiency formula is expressed, or efficiency, I should say, is expressed as a percentage and doesn't have any units, and that's because the formula cancels the units out themselves. So the formula is expressed as the percent efficiency is equal to the energy output over the energy input multiplied by 100. Now, because energy is always lost to heat, so I'm going to circle this here, the energy output is always less, so smaller than the E input, and that's because energy, specifically potential, but in general, energy is lost to heat. And heat is just a form of thermal energy. So in a problem, how can you tell if you're given two energies or if you have to find two energies, which one is the energy input and which one is the energy output? Just look for the one that's less. The one that is less is going to be your energy output, and the one that is more is going to be the energy input. One last thing too is that each of these are in joules, so your output and input would be in joules, but because like terms you would cancel it out, that's how we get a percentage in our final formula. We could also express energy in terms of work. So remember that work is really just a change in energy. So we could also have efficiency equal to the work output divided by the work input. And how do we know that we're dealing with the work formula versus a regular energy formula like potential or kinetic energy? Well, remember that work is usually going to have an applied force, right? So an applied force, and that's going to be measured in newtons. So if we see anything given in the question that has the units in newtons, we know that we're probably using the work formula. So our first example reads, a crane moved a 200 kilogram hot tub from the ground to the top of the hotel 53 meters above the ground. If the crane used 200,000 joules of energy, how efficient was the crane? So in this question, we could kind of see, just because it says used 200,000 joules of energy, that sort of indicates that it's the input, but let's numerically prove it. Remember that the output is always going to be less than the input. So we have a mass, we have a height. That means that we can find the potential energy. So we're going to go PE is equal to mgh. And we're going to go 200 kilograms for the mass that was given above, multiplied by 9.81 meters per second squared, multiplied by 53 meters. That gives us a total amount of 103,986 joules of potential energy. And since this is less than the 200,000 joules that it used, then we know that this is the output, and then this must be the input. So with that in mind, we now have enough information to solve for the efficiency of the crane. Using the formula, we get an efficiency percentage of about 52% when we include the appropriate number of sig digs. Actually, in the question, it's just say 200.0. And this one is 0.0 as well, 52%. Let's look at another example. The second example reads, what is the efficiency of a block and tackle if you pull on 20 meters of rope with a force of 600 newtons to raise a 200 kilogram piano 5 meters? So the minute we see the force here, we know that this is going to be the work formula. And that this here specifically is the applied force. So we're going to use the work is equal to the force multiplied by the distance. In this case, it's going to be 600 newtons multiplied by 20 meters here for the distance of the rope. And when we do that, we have about 12,000 joules. And remember that work is really just a change in energy. So there could be cases where we use work as the output and the input, or work as an output or an input, and energy, potential energy, as an output or an input. In the end, because they both give us the same units, they're very interchangeable. So what we're going to do is, because I'm given the mass of the piano and a height, I can actually find the potential energy as my second source of joules. So we go PE is equal to mgh, which is then equal to 200 multiplied by 9.81 multiplied by 5 meters. And when we plug in all the variables in the potential energy formula, we get a value of 6,810 joules. So by the concept that the lower energy is always going to be the output since it loses energy to heat. So this over here, we're going to label as the output. Now we have an output and an input. So we can go ahead and use the efficiency formula in order to calculate the efficiency. My apologies, that should actually be 9,810, not 6,810. So make sure that you actually correct that. Regardless, it's still going to be the output, and 12,000 joules is still going to be the input, and that gives us an efficiency of about 81%.